Okay, in this screencast, we ask ourselves what would have happened if instead of saying, here's how triangles are congruent, we had gone a different way, a way that's a little bit more consistent with Klein's Erlanger program. What if we had decided to take a look at everything in terms of transformations? And some of the authors of the Common Core State Standards for mathematics wanted this front and center in the Common Core now next gen state standards. So we build the geometry in exactly the way we imagined building the geometry. There's more than one point. Every 2 points determines a line. Every line is a number line. Uh, Lines break the plane up into half planes, exactly the way we envisioned. Angles are a thing. But then remember, Axiom 6 was that SAS thing, and that felt a little weird. What if Axiom 6 is this one? What if we swap out side angle side with the reflection postulate? What if we say line reflections are a thing? Now, mind you, we only need line reflections to be a thing because rotations, translations, they are all compositions of reflections. Reflections, as we've proven, are all you need to get every isometry in the plane. So what if we do this instead? Well, then our notion of congruence changes. Our notion of congruence involves two figures being congruent if and only if there is an isometry that maps the one onto the other. And that's how transformation-based proofs work. We prove that triangle ABC is congruent to triangle DEF. We say that triangle ABC is congruent to triangle DEF if there is an isometry, and we know that a composition of isometries is an isometry, if there is an isometry such that A maps to D, B maps to E, and C maps to F. That's how we show that triangles are congruent, for example, in a transformational way. So if we take this on instead of side angle side, does side angle side still hold? What if this happens? Are those triangles congruent using the reflection postulate? Well, yes. So here's the rough idea here. We construct segment AD. It has a perpendicular bisector. We reflect triangle ABC over this perpendicular bisector. If we do that, A prime is D. This almost makes sense. B prime ends up somewhere over here. C prime ends up somewhere over here. And you get this triangle like this. Gosh, that's hideous. But that's the rough idea. So then what? And this angle is congruent to that angle, and those are congruent, and those are congruent by properties of isometries. This is going to be really hard for you to see if I don't draw this well. So I'm going to take the time and draw this better. B prime has to end up over here somehow. And C prime has to end up over here somehow, right? So that this looks a little bit more like that triangle over there. Those are congruent, those are congruent, those are okay, that's a little better. So now what? Well, now, so this is line L, which is the perpendicular bisector of segment AD. Then we draw line M. Oh, golly. Then we draw line M, and line M is the angle bisector of angle C prime DF. It's the angle bisector of angle C prime DF. So what does that do for us? How do we proceed? We want to show that C double prime is F. Well, how do we do that? Well, we know that if we reflect the sides of an angle over the angle bisector, this side ends up here and this side ends up here, right? We know that because isometries preserve angle measure. So whatever this angle measure was before the reflection, it's this angle measure on the other side, right? We know that we know that isometries preserve angle measure. Now, what does that mean? That means that this ray, the ray A prime C prime, lands on the ray DF after the reflection. We know that C double prime ends up somewhere on this ray. Where on this ray? Well, because A prime C prime is congruent to AC, which is congruent to DF, we know by the ruler postulate that C double prime has to land right here. So it's the angle bisector plus the ruler postulate that forces C double prime to land there. So then C double prime lands here. B double prime ends up somewhere over here. We're not sure where. It turns out that if triangle ABC and triangle DEF have the same orientation, then these two reflections will do the job. B double prime will end up on E. If not, then reflecting over the perpendicular bisector of B double prime E will do the job and finish off the congruence. So if we postulate reflections, we get side angle side. We get it. If we don't get, so it does not matter if we choose side angle side as a postulate or we choose reflections as a postulate. Whichever one we show, the other one works because of it. So some people set up their geometry this way, where they think that transformations are very intuitive. We're going to use transformations to get people around the plane, to get points around the plane, to get congruence in the plane. That's great. That's fantastic. It is an acceptable approach. It is mathematically rigorous. I'll have some more examples on how to prove things transformationally in another video. Great.